Welcome to the lecture on stability and steady state error. So, in the previous 3 lectures, we have discussed about stability. In the 2 lectures, and that is this lecture and the next lecture, we will discuss about steady state error. So, we have discussed that to design a control system, there are 3 objectives, that is the transient response and stability and steady state error. So, we have discussed the transient response and we have discussed stability. Today we will discuss about steady state error. So, we know that steady state error is the difference between the input and the output for a prescribed test input as time t tends to infinite. So, here we can say when we check about any system, check about steady state error for a system, we use certain prescribed test inputs. So, these test inputs could be step input, they could be ramp input, parabolic or impulse input, and these different inputs, when they are input to the system, we study the output of the system against this input, and we define the steady state error in that condition. So, when we remember that when we had the elevator response, so if we remember here we had time t, we have this floor number 4, let us say we are at 0 or ground floor, and we press this button number 4 to reach that 4th floor, the elevator response will start like this and it will be like this. So, of course, this part we show, this is the transient response, and this is the steady state response, and this difference, that is the difference between the input, because our objective was to reach at the 4th floor, but the lift or elevator reaches with little difference. So, it did not level with the floor of the 4th floor. So, this is difference is there was steady state error. So, today we will discuss that how we can define this, how we can define the test inputs, and how can we define a system or design a system so that we can reduce the steady state error. So, here we have the test inputs that we talk about, this step input. So, we have here, this is the step input, so time, and here we have, let us say we have the input RT with time. So, this is constant, or if you give this value 1, that is unit step. So, if this is 1, so this RT equal to 1 for all the time greater than 0. So, if we take RS equal to, if we take the Laplace transform, that is 1 by S. So, we know that this step input can be used to for the control system to monitor the position, stationary position of some part or some component. So, for example, if there is some, for example, this lift, we press this 4, and this is a system whether it is following this position or not. So, we can use this step input for testing as a test input for this kind of system or this kind of application. Now, second input comes as the ramp input. So, here we have ramp input. So, what is ramp? So, ramp is the linearly varying input with time. So, here is time t and this is RT, and the input is linearly varying. So, it is have constant slope. It is not the constant, but it has some constant slope. So, here we can say that dRT by, so RT we can write as it is function of time t with some constant. So, here we take the Laplace transform. So, Rs, Rs of this is S is 1 by S square. So, here we will have 1 by S square this Laplace transform as Rs. So, such an input this kind of input can be used to monitor a system that is have constant speed. For example, if there is some satellite orbiting satellite, and because its angular speed magnitude is constant, but it is orbiting, so we can use this input to monitor the angular speed of this input. So, this test input can monitor the some changing position with constant velocity. Now, there is the third type of input, that is parabolic input. So, the parabolic input we have parabolic input. So, we have here RT, and this is something like parabola here, and here this RT is, let us say this is a parabola half t square, and so its Laplace transform is 1 by S cube. So, this type of test input can be used to monitor the accelerating objects or some object that is accelerating, and we can use this test input to monitor the acceleration of that object. For example, we launch some missiles, and because missiles are accelerating objects, they have to accelerate to hit the target. So, we can use this type of input to monitor the acceleration or accelerating objects. So, we see the importance of these three inputs. So, step input to monitor the stationary position, the position changing with constant velocity, and this position changing with constant acceleration. So, we will study the steady state error against these three type of inputs, three types of test inputs. Now let's see some output against these inputs and how we can define the steady state error against these different type of inputs. So here let's we give some input here. This is input or desired output, that is a step. This is a step input, and we are getting the response of our system. So let's say we are getting something so this is output 1, this is output, and let's say output 1. Now we have another output, output 2. So this is output 2. So here we can see that this output 1, the steady, it is starting following this after the transients are decayed, it is following the input perfectly. So here the steady state error is 0. So in this case output 1, so steady state error is 0 because it is matching to the input. Now if we see output 2 and this difference we call it E2 infinite. So when time tends to infinite, the difference is constant. So output 2, there is some finite steady state error here. So for output 2, there is some finite steady state error. Now let's see the ramp input. So here T, this is CT, and we have some ramp as input. So this is our input. Now here so this is output 1. This is output 2. And this is output 3. So here we see that this output 1 is finally going and meeting or to the input. So here output 1 has 0 steady state error. Output 2 has, so this is finite steady state error, let's call it E2 infinite. So finite steady state error, and this is parallel to this, so slope is same. Here also the slope is from here it is same. Now see the output 3, its slope is different, and the the it is not tending towards the input, and this they are more diverging. So here this is infinite steady state. This can be called as infinite steady state error. So now let's obtain. So these things we can see here in this diagram what I discussed. We can see here the same thing that I explained. Now let's find that how we can define the steady state error in Laplace variable form, that is S form in terms of S, because we are dealing with the transfer function and we should know how to compute the steady state error in terms of if the function is in S domain. So we define the steady state error. So we have some general transfer function that we are discussing is, here is GS, there is input RS, and here is we are getting CS, the output, and we give feedback. Let's say we call unity feedback here, and we give here this, and here we get the ES. So this is plus, this is minus. So this is a unity feedback system, and here we can write ES equal to RS minus CS, and CS equal to GS into ES. So we can write this as CS by GS equal to RS minus CS. So from here so ES equal to RS minus CS, we can write GS into ES. So we can write ES 1 plus GS equal to RS, and so ES equal to RS upon 1 plus GS, because this is the error function that we can find. So the final value of the error, so E infinite equal to limit Et when t tends to infinite. This is the definition of the error, that when time tends to infinite, the difference between the input and output is called the steady state error, and this can be written as limit S ES S tends to 0, and therefore here this error we can define equal to limit, so S into RS, because we can replace this SRS upon 1 plus GS, and this S tends to 0. So now here we can compute the error, steady state error. With this we know input, we know the transfer function, we can calculate the steady state error. Now here we should know that when we talk about steady state error, so steady state error is only valid when the system is stable. because if the system is not stable, the response will not reach to steady state response, and there is no meaning to talk about the steady state error. So therefore, for any system, we must first check whether it is stable or not, then only we should calculate the steady state error. So now let's see if there is step input. If we have step input, so it means the Rs is equal to 1 by S. So we can calculate the steady state error in finite, that is equal to limit s tends to 0 s into 1 by s by 1 plus gs. And so this is here cancel. So 1 by 1 plus gs limit s tends to 0, because this limit will reach to the function that contain the s, or the function gs is the function of s. So if we want 0 steady state error, because our objective is that there should be 0 steady state error, so there should not be any finite steady state error. So if this term tends to infinity, this part tends to infinity when s tends to 0, so this is infinity, then this term will be tending towards 0, right. So to find this 0 steady state error, limit s tends to 0 gs, so it tends to infinity. And therefore gs must take this form s plus z1 s plus z2 into s power n s plus p1 s plus p2 into some other. So you see here gs is in the form, so these are the zeros, because this is gs is a transfer function, so it could have some zeros, and these are the poles. But there should be one more, this term Sn here, because when s will tends to 0, this term there, this if there is s, even single s, it will make this term to infinite, and when this will be infinite, this error will be tending to 0. So therefore n must be greater or equal to 1. If we want in a system that against step input it should have 0 steady state error, the gs should be in this form and s should be at least 1, and at least n should be equal to 1. So there should be at least one s. So this 1 by s is, it means this is the integration, this is the Laplace transform of some integration. So there should be one pure integrator in the circuit or in the forward loop. So if there is one pure integrator here, 1 by s, then this transfer function is 1 by s into this gs, and so the steady state error will tend to 0. Now if n equal to 0, suppose here if n equal to 0, then we will get no any s term, and so this term gs will be here, and so we will get z1 into z2 into zeros into poles, and so these terms will be 1 by 1 plus z1 into z2 into z3 by p1 into p2 into p3, and so this is finite term, and this is finite. So 1 plus this finite is finite, and this complete term is finite, and so we will get steady state error as finite, because we remember that we against the step input we had two type of output, one was this and one was that. So this error E2 infinite, this was finite error and this was zero steady state error. So we will get this output with finite error, and when we have at least one S here we will get this one. Now come to the ramp input. So this was step. Now if we have ramp input, suppose here we have ramp input. So for this ramp input we have Rs, we know that Rs equal to 1 by S square. So we get E infinite equal to limit S tends to 0 S into 1 by S square upon 1 plus Gs. So here 1s will cancel out this square term. So we will get limit S tends to 0 1 by S plus S Gs. And equal to 1 by SGS limit S tends to 0, because this will be 0, and so we will shift this limit to SGS. Now to have zero steady state error, this limit S tends to 0 SGS tends to infinite, and therefore so it should be this, and therefore here the Gs must be in the form S plus Z1 S plus Z2 S plus P1 S plus P2. Now here should be some power of S. So S power n. Now we know that n should be greater or equal to 2 here, because if n equal to 1, so there is only one S, this S will be cancelled out with this S and we will get a finite. So if n equal to 1, so n greater than 2 we will get 0 steady state error. If n equal to 1 we will get, so n equal to 1, this S will cancel out with this S, we will get here. So P1, P2, P3 upon Z1, Z2, Z3, this steady state error we will get. So this limit S tends to 0 SGS will be equal to Z1, Z2, Z3 upon P1, P2, P3, and then when we put, we will get steady state error as P1, P2, P3 upon Z1, Z2. So this is a finite steady state error. And if n equal to 0, so n equal to 0 means we will get this term S into Gs. So limit S tends to 0 S into Gs, and n equal to 0 means here is only this term and this term multiplied by S, so this will be 0, and when we put this as 0 we will get infinite. So here infinite SS error we will get. Okay, so we would like to stop here, and these we can see that these figures we took from the book of Nice Norman S. Control Systems Engineering, and so we discussed about steady state error for step and ramp input. We will continue this for parabolic input in the next lecture. So I stop here and see you in the next lecture. Thank you.